Hi everyone, I'm Junru from Alibaba Cloud. Today I will present our work, PolarStore, high performance data compression for large-scale cloud native database. Next, I will first introduce the background and the motivation. Let me start with the background. PolarDB is a cloud native relational database. It uses storage compute separate architecture. In this architecture, we have a read-write node that handles write requests, multiple read-only nodes for read queries, and a shared storage layer at the bottom. The key benefit of this architecture is the elastic computing scaling. Users can scale computing resources up and down without any data migration. This significantly reduces computing costs. However, storage cost remains a critical concern for our users, especially during periods of low activity. Therefore, data compression becomes an effective way to reduce this storage cost. From our users' perspective, there are two main concerns about compression. First, compression ratio. Users want highest possible compression to save money. For code data and snapshots, they want to even higher ratio. Second, the performance. Users cannot tolerate any degradation on latency-sensitive operation, specifically redo log write and the page read latency. And importantly, compression should not consume extra CPU resources on computer node because these resources are billed to users. So our question is, how do we achieve high compression ratio without any performance overhead? There are three key dimensions to consider. The first is the compression input size. This means how much data we feed into the compressor at a time. The second is the compression algorithm. This ranges from lightweight algorithm like LZ4 to a heavy algorithm like gzip. The third is the index granularity. To understand this, think of the space before compression as the logical space and the space after compression as the physical space. With compression, the system needs to maintain an index that maps the logical space to the physical locations. The index granularity defines the smallest unit that mapping. In other words, it defines the smallest piece of compression data that can be independently located and read. For the compression input block size, a larger block gives a compression algorithm more information to work with, so it achieves a higher compression ratio. But it also introduces extra amplification and extra compression and or decompression overhead. On the other hand, a smaller block enables better random access, but gives a lower compression ratio. This is a foundational trade-off between compression ratio and performance. The second dimension is the compression algorithm. Software-based approach offers flexible compression parameters and dynamic configurations, but they come with lower performance. Hardware-based approach like FPGA or QAT provide high performance, but they are limited to fixed configurations. Again, this is a trade-off between compression ratio and performance. The third dimension is index granularity. Byte leveling is space efficient, but it requires complex garbage collection and space management. 4 kilobyte level indexing is simple, but it wastes space compared to byte level indexing. This is another difficult trade-off between compression ratio and performance. Now let me show the exciting approach in original PolarDB. The first one is B+3 compression at the database layer. It takes 16 kilobyte input. You use flexible software compression, but index at 4 kilobyte granularity. The problem is that the 4 kilobyte indexing leads to space fragmentation and a suboptimal compression ratio. The second approach uses computational storage drives, or CSD. CSD compresses a 4 kilobyte input block and use byte level indexing handled by the variable length FTL. It achieves excellent space efficiency with zero software overhead. However, the input size is fixed at 4 kilobytes, and the compression algorithm is not flexible. Therefore, neither approach can break the trade-off. This brings our key idea, dual layer compression. As shown in the figure, layer 1 is the software layer. It compresses 16 kilobyte pages into n blocks. It supports flexible input size and allows the user to choose LZ4 or CSTD per page. Layer 2 is the CSD hardware layer. It further compresses these 4 kilobyte blocks into better aligned physical blocks. The variable length FTL handles bi-level indexing without software overhead. Dual layer compression is the core design of our system. Furthermore, since our storage only serves PolarDB, we can do many database-specific optimizations. Before going into the details, let me first talk about two key I/O metrics we care about. The first one is the read log write latency, which directly affects transaction commit. The second one is the page read latency, which affects query performance when we have a buffer pool miss. Based on these two metrics, we designed the three optimizations. The first one, we bypass compression for read logs. We use a non-compression flag combined with a high-performance SSD, such as Optane SSD. This works well because read logs are small and frequently recycled. The second one, we do adaptive algorithm selection between LZ4 and CSTD for each page to get better page read latency. And the third one, we introduce a per page log mechanism to solve the long tail latency problem in page read. Let me explain the second optimization in detail. Here is the key observation behind the design. Because of 4 kilobyte alignment, even a tiny size difference between can save a whole I/O block. Look at this example. LZ4 compresses a page into 4097 bytes. That needs 8 kilobytes for all I/O, but CSTD compresses the same page to 4096 bytes, just 1 byte less, and it only needs 4 kilobytes of I/O. That single byte saves 4 kilobytes of I/O, which easily outweighs the STD higher decompression cost. So in this case, we use the STD. But now look at the in other side. LZ4 compresses 4095 bytes, that needs 4 kilobytes of I/O. CST compresses 2000 bytes, also 4 kilobytes of I/O. CSTD saves 0 I/O here, but wastes the CPU on decompression. So in this case, we choose LZ4. So neither algorithm is always better. The best choice depends on each specific page. Our decision run per page during page writes, not on the read path. If CPU utilization is about 20%, we just default use LZ4 for lower head. Otherwise, if the page has more than 30% update content, we try both algorithms and compute the benefit to overhead ratio. If the saved bytes per extra microsecond of decompression exceeds our threshold, we pick the STD, otherwise we pick LZ4. This threshold comes from the fact that saving 4 kilobyte I/O reduces and read latency by about 20 or 14 microseconds. Now let me explain the third optimization, the per page log design. In the normal case, when a page read arrives, the storage node reads the page from disk in a single read. But in the worst case, the old page needs to be updated with new read logs. If these logs have been evaded from memory and are scattered across different locations on the disk, the storage node needs multiple disk reads, 5 or more, to gather all the logs. This causes high tail latency. Our solution is simple. When read logs are about to evade from memory, we proactively merge all logs belonging to the same page into a dedicated per page log space. Now, when a page read arrives, we only need 2 I/O reads, one for the old page and one for the per page log. This is because we pre-merge them into the per page log space as a background process. Now here is a critical point of the per page log design. Allocating an extra 4 kilobyte space for database page would waste 25% of space on a normal SSD, but the CSD compresses the unused portions of this per page log space. So actually, actual physical overhead is minimal. This optimization is only feasible with the CSD. That covers our architecture design. Now let me share about what we learned from deploying it at scale. First, the hardware redesign. On the hardware side, the first change is the FTL. PolarCSD 1 uses host-based of FTL with an open channel architecture. While this made software iteration easier, it caused a serious problem at scale. The first problem is stability. We observed many slow IOs exceeding 1 second, with some exceeding 10 seconds and lasting more than 10 minutes. And some kernel bugs brings down the entire server. The second problem is resource consumption. The host-based FTL consumed 184 gigabytes of memory and 24 CPU cores per server for just 12 devices. Because of this overhead, we had to disable software compression and limit deployment to only 10 devices per server. PolarCSD 2 fixed all of this by moving to a device management FTL. This means zero host CPU and memory contention, and device features are contained to individual devices rather than affecting the entire server. The second change is the PolarCSD 2 is the maximizing the compression ratio. The average hardware compression ratio in our environment is about 2.5, but the PolarCSD 1 only achieved 2.4, which leads to waste physical space. To close this gap, we need to allocate more space for index to achieve a higher compression ratio. Beyond host level stability, we also encountered a cluster level challenge. The left finger shows the distribution of compression ratio across storage nodes in a cluster, and the right one shows the physical and logical space distribution. The compression ratio varies widely for 1.2 and to 3.8. This creates a problem. Disk become full for different reasons. Nodes with below average compression ratio run out of physical space first, and their logical space is wasted. Nodes with above average compression ratio run out of logical space first, and their physical space is wasted, because they don't have enough index space to take advantage of the higher compression ratio. In either case, usable complexity is wasted. To address this imbalance, we development a compression-aware scheduling strategy. Our solution is as shown in this figure. We plot each storage node with logical space on horizontal x and physical space on the vertical x. This divides nodes into 4 zones. Zone A has plenty of physical space but limited logical space. These are high ratio nodes. We migrate low ratio chunks out to the reliable and logical pressure. By rebalancing chunks based on their compression ratio, we make sure both logical and physical space are used efficiently across the cluster. Now let's look at the overall results in production. Our compressed storage have over 20,000 CSD devices, managing over 100 gigabytes of data. In this paper, we use 4 clusters in PolarDB to show the benefits in both performance and compression ratio. Cluster C1 uses PolarCSD 1 with software compression disabled. Cluster C2 uses PolarDB CSD 2 with all techniques enabled. And we compare them with 2 normal clusters, N1 and N2, which use normal Intel SSD with the same hardware setup. Cluster C2 with PolarCSD 2 and dual layer software compression achieves a compression ratio of 3.55. The cost per physical gigabyte in 1.32 but the effective cost per logical gigabyte dropped to 0.37. This is about 60% cost reduction compared to normal SSD. The natural follow-up question is, does this compare hurt performance? The figure shows the Sysbench throughput across 7 workloads. C1 uses PolarStore with hardware-only compression, shows some performance drop compared to the uncompressed baseline N1, but C2 uses PolarStore with dual layer compression, achieves similar performance to uncompressed cluster N2. Let me summarize our 3 key contributions in our paper. First, the dual layer compression that combines software flexibility with hardware efficiency. Second, 3 database-oriented optimization targeting the 2 critical I/O paths in database. And third, practical lessons and solutions from large-scale deployment. Thank you for your attention.